And welcome to Chapter 2, Part 5. We've had an introduction to resonance now, and so we want to get a strategy for coming up with additional resonance structures. And we'll talk about in the future why these resonance structures are important, how they can aid us in figuring out how certain functional groups will respond in different reactions. But for now, we need to figure out a way to get from one resonance structure to another. And so Klein gives us a good starting point, and we look at these 5 different patterns. Now, each of these patterns will be covered in its own slide or two, but I want to make sure before we get started that we talk about this word, allylic. An allylic position is a position next to a double bond, right? So this is an allylic carbon. This is an allylic positive charge. If we had, let's say we had a negative charge, this would be an allylic lone pair. So it's not in the double bond, but it is one atom over. And it's very important, and it gets its name because you're going to see the different patterns in resonance. Being in that allylic position puts you in the right place next to pi bonds and, those overlapping p orbitals. And a lot of times will allow that atom, that charge, that lone pair to participate in the resonance hybrid. And so you see allylic lone pairs and allylic carbocations are first up in our pattern recognition. So I just wanted to make sure that we understand the allylic position. All right. Okay, and of course it's on the next slide. So the allylic positions next to a double bond, as opposed to the vanillic or vinyl positions, which are actually in the double bond, right? So if we're thinking about all the carbons in this example, the carbons in the double bond are vinyl carbons. The carbons right next to the double bond are allyl or allylic carbons. And you can see when we are going to talk about lone pairs, like the lone pair on this lower nitrogen is just one atom over from the double bond, making it allylic. This one is too far away, so it's not allylic. And that will be significant when we are looking for resonance structures. So pattern 1, right, is allylic lone pairs. So it can be a lone pair of electrons on a carbon, on an oxygen, on a nitrogen, there are some, those would be vinyl lone pairs. It can be on a nitrogen. The double bond can be between 2 carbons. It can be between a carbon and an oxygen or carbon and a nitrogen. It just has to be a lone pair on an atom next to a double bond. And that pattern is going to require 2 arrows. So in the most basic, and I will just start with the one they start with, we have an allylic anion. The lone pair is you're going to always start your arrow at the electrons, and it's going to move away from that carbon. Now, not far. It's going to form a double bond, and you have to remember that this carbon in the center has a hydrogen. So we can't just form a double bond there. We have to push the other double bond, the other pi pair of electrons, over, right? And that can happen because this carbon only has 2 hydrogens. And that will allow us, right, if we draw the result of this, we now have a new double bond here on the right. We didn't break a sigma bond because that was against the rules, but we did break that double bond, and we put a lone pair on the carbon on the left. So now the negative charge is on that left-hand carbon. All of the atoms are still arranged in the same order. We've only changed the location of electrons, Both molecules have an overall -1 charge, so we haven't broken any rules of resonance. You can do this with each of the examples on this slide that we are looking at. I'm not going to do all of them, but I do want to show you how this can work even if you have, say, let's see. I'm going to go with this example. Even if you're starting with something neutral, right? For instance, this is a neutral molecule, but we have an allylic lone pair. We have lone pairs on this oxygen here, and it is one atom away from the double bond. So it's the same pattern. You draw your arrow going from the allylic lone pair towards the double bond. We want to avoid putting 5 bonds on that carbon, so we move the pi bond electrons out. So it's 2 arrows flowing from the allylic lone pair to the other side of the double bond. So we could draw now the result of this. We've drawn a double bond here. Now there's only 1 lone pair, right? Because 1 lone pair turned into the double bond. We have a single bond now going up to this oxygen. It had 2 lone pairs, and now it has a third one that we moved out from the double bond. Now, what's important to note to complete this resonance structure are formal charges. This is overall neutral, so this one is also overall neutral. However, our oxygens have no formal charges in this structure, but we have a negatively charged oxygen and a positively charged oxygen here. Again, it's important to recognize those common bonding patterns. I'm not going to go through each one of these, but you can see the arrows laid out for you in each one of these. And you see this is a very predictable pattern. The arrow starting on the allylic lone pair, going in and forming a double bond, the pi electrons moving out and forming a lone pair on that outside atom. And you have all of the resonance structures for those practice problems on the previous slide. Definitely recommend you running through some practice here. I remind you periodically, as that's what I would do in class. You can jump into that Wiley Access, go straight to section 2.10, and have access to skill builder type problems right within the chapter. Getting on to pattern 2, we are now looking at allylic carbocations. So now, instead of a lone pair in the allylic position, we have a positive charge. We saw this in our very first example here. Now the arrows, instead of starting at the allylic position, start at the double bond, because remember, arrows show where the electrons are to where they are going. A positive charge is a lack of electrons. So you're never going to have an arrow start on a positive charge. It may end there, but it'll never start there. Now the allylic carbocation often only needs 1 arrow. Right? So we are taking that pi bond and we are shifting it over. Right? So we saw that example a lot in the last video. Oh, no. Over here now. You also see over here, very similar problem. And it's a good example of how we frequently will have more than 2 resonance structures. All right, so we have a plus charge, and it is in an allylic position. So if we move that pi bond, right, and it can only move over 1 position. It's got to be an allylic cation. That will, and let's draw what story we're telling here with that arrow. So we have a new double bond here. We didn't touch this one. We've now left this carbon right here that just has 1 hydrogen with a plus charge. Now that's created a new allylic carbocation. So we can do it again, right? If you just go 1 step at a time, you can often find that you have multiple resonance structures. Now, what's interesting about that is the positive charge is delocalized not only to 2 carbon atoms, but to 3. It's making it even more stable, right? The more resonance structures you can draw, the more stable that ion is going to be. Pattern 3, right? So we had allylic lone pair, allylic cation, allylic, plus charge. And pattern 3 is going to be a lone pair adjacent, right? So electrons that are more free to move adjacent to a plus charge, right? So you have electrons on one atom next to an atom that is lacking electrons. So electrons, again, always moving from where there is more to where there is less. And we see this in a few different examples here on this slide. For instance, it's very easy to sort of visualize when you have a negative and a positive. Well, electrons are going to go from, again, where there's more, where it's negative, to where there's less, where it's positive. And so you see that pair of electrons moving down, creating that double bond, right? So the lone pair is making a double bond with where you had a plus charge. These are both overall neutral, right? This also works in that next example where you have an ion, right? So in this example, you have a plus charge on the carbon, and a lone pair can move towards the plus charge. Again, it's got to be adjacent. Can't be a lone pair from just any old place in the molecule. It has to be an adjacent atom. And that will give us a double bond here. Now, what's important to note, that carbon only had 1 hydrogen. It still has 1. So now its formal charge is 0. The oxygen had 2 lone pairs. Now it has 1. Its formal charge will be plus 1. So each one of these is still overall plus 1. Pattern 4 can be really useful if you have a neutral molecule and you really don't know where to go. So pattern 4 is using a double bond. You'd also use a triple bond, but more frequently you're going to see double bonds between, and we'll say double or triple. It's just got to be a pi bond between different elements. Since most elements have different electronegativities, you can just say different elements. So you don't want to take a carbon-carbon bond, double bond. There's not going to be a pull on the electrons here, right? Those 2 carbon atoms are going to be sharing those electrons pretty evenly. So splitting that double bond up doesn't make much sense, and it would give you 1,000 very minor resonance structures. So you want to stick to double and triple bonds between 2 different elements. And you want to go, and to show the pattern when you're trying to get 2 resonance structures, you always want to take the electrons from the double bond to the more electronegative element. Right? So when you're thinking about the periodic table, the closer to fluorine something is, the more electronegative it is. So oxygen's more electronegative than carbon. So a resonance structure with common bonding patterns, right now we have oxygen with 1 bond and 3 lone pairs. We have carbon with 3 bonds and no lone pairs. This is a resonance structure. It may not be as strong of a resonance structure as that neutral one, but it is important. The reality of this molecule is a hybrid. That oxygen has more electron density around it than carbon. And this is just another way to show that through resonance structures. And lastly, pattern 5, we are looking at conjugated. Now, what does that mean? That means that we have double bond, single bond, double bond, single bond, alternating all the way around. So conjugated pi bonds in a ring. for now, you're just going to be looking at that 6-membered ring, the aromatic structure. These are known as Kekulé structures, right? And this structure has been known for ages and ages. And we know that those double bonds are delocalized. We know this because if we measure each of the CC bonds in the ring, they're all the same length. They are all about a 1.5 bond length. This is a flat structure. It has very different reactivity than any other double bond. It's very stable, and it is because those pi electrons are shared over the whole ring. That's probably the easiest one to just plop down if you're asked for another resonance structure, is to just alternate those rings. You can put your arrows in, and you have to put all 3, because if you only move one at a time, you'll put 5 bonds on carbon, and then I'll have to yell at you. And so here's just a summary. Now, I highly recommend doing some practice in this section before you go on to do, just random resonance problems. I do have an extra resonance problem worksheet up on eCampus for you, but I would do some practice with these patterns first. Now, let's go ahead and do a practice problem here at the end of this one, just so we can take a larger, more interesting molecule, and I'm going to kind of blow this one up here. There is not one place to start. There are lots of resonance structures for this molecule, and we can practice using a bunch of our patterns that we just learned. So already I see some allylic lone pairs. So these lone pairs on the oxygen are in an allylic position. I know I can move an allylic lone pair and form a double bond, and then take the electrons in the double bond that is existing and move them out. And this allows me to draw, and I'm going to come up here and draw it here. I try not to make you guys draw 7-membered rings too often. If you're already annoyed at having to draw so many hexagons, I promise you a heptagon will make you real mad. I've done it for a long time, and mine still look like this. And so if I draw what I have based on these arrows over here, I have a lone pair on that carbon, and I have a double bond out to the oxygen with 2 lone pairs. Now, the negative charge is not on the oxygen anymore. The oxygen is 2 lone pairs, 2 bonding pairs. The carbon that got the lone pair, that's where the negative is now. Now, to find another resonance structure, say I asked you to find 3 resonance structures. I can look at this new one that I drew. I can look at the original. I just want to make sure that I don't repeat myself, right? I wouldn't want to go, oh, look, now I have an allylic lone pair, and then go backwards. I want to find a different resonance structure. So let's say, oh, and don't do what I did. There's still a positive charge right there. So I can do a couple different things. I have a lone pair next to a positive charge now. I have 2 different lone pairs next to a positive charge. And it doesn't matter which one I can start with either one. Let's say I want to move this lone pair that I just created and form a double bond with the carbon that has a plus charge. Well, let's see what that would look like. Nitrogen still has a lone pair. Nitrogen, that still has a double bond. Sorry, I have to talk myself through this while I work. I created a new double bond here and an oxygen here. I mean, not an oxygen. That's all still the same. Now look how interesting. This carbon has 4 bonds. It had a plus charge, so it had 1 hydrogen. This carbon has 4 bonds. It had no hydrogens on it. And they're both overall neutral, but this one doesn't have any formal charges. If I wanted to come up with, say, a third or fourth resonance structure, there's still a few other patterns I could look at. All right, I have a double bond between two different atoms. Nitrogen is more electronegative than carbon. I could move a pair of electrons out. Right? There are lots of options here. I will not be drawing every single possibility for this particular molecule. That puts two lone pairs on that nitrogen, so that nitrogen is negative. Sorry, we're still going to talk to ourselves while we draw this one. There we go. Well, I know that this molecule is overall neutral, so if I created a negative charge, there better be a plus charge somewhere. Well, this carbon only had one hydrogen. And when I move that pair of electrons, I don't just magically get another hydrogen. So this carbon has to have a plus charge on it because it only has 3 bonds. All right, so lots of molecules have various patterns you could use. Just do one at a time, and most any graded work you have, you will be asked for a certain number of resonance structures. I'll never just give you a problem and say, draw all the resonance structures. I'll ask for 1 or 2 or 3. And I believe your homework will be the same. And now, that is where we will end. In part 6, we will assess resonance structures. Because as you might notice here, these are not all the same. All right, some resonance structures have formal charges, some do not. And so we will talk in more detail about that in part 6.